In this segment, we'll finish our look at the example list struct, and we'll introduce several more C language concepts related to larger code. So let's start with the idea of a free list. Allocating and freeing nodes, malloc and free, is very time expensive because the management of the runtime heap is complex. Now, to reduce this expense, some programs maintain their own private recycling system for commonly allocated types, like our node struct. Whenever we would free a node, we might instead keep track of the unused node ourselves without releasing it. And then later when we need a node, we could first use one of our tracked unused nodes, if we have any, and then resort to an actual malloc call only if there are no recycled nodes available. So how would we track unused nodes? Well, the simplest way is to chain them all together in a list. This would not be a list of actual data. It would be a list of unused nodes awaiting reuse, and it's called a free list. We don't care about the data in the nodes on the free list. It's just a parking lot for unused nodes, a string of empty bottles, figuratively speaking. When we no longer need a node, we add it to the free list instead of freeing it. And if the free list has nodes on it, then when we would allocate a node, we instead take one from the free list and use it. If the free list is empty, we malloc the node in the usual way. Once we get a free list going, if we're freeing about as many nodes as we allocate, we'll get what we need from the free list and rarely do an malloc call. Taking nodes on and off the free list is much faster than malloc and free because those functions must deal with any size of allocated block. They have to maintain the elaborate headers and other runtime heap data structures for doing that. If we're allocating and freeing many instances of exactly the same type, then a free list is much faster. So let's modify our list.c file to use a free list and illustrate some design ideas along the way. A free list, like any list, needs a head pointer. Now, at first glance, you might think we would add the head pointer, let's call it free list. You think we might add it to the list structure up here in list.h. Now, doing that would in fact work, but it would mean that each and every list would have its own free list. And if one list had nodes to spare on its free list, another list would not be able to take advantage of them. Better to have a sort of community recycling system with just one free list head pointer pointing to a single free list that is shared by all the lists and can be drawn from by any list when it needs a node. So, question 1. If we want a shared list of reusable nodes, where and how would we declare free list its head pointer? Where would we put the declaration of node star free list? So, coming back from a pause on that, the thing we really need to do is make free list a global variable, and of course a static global variable, in our list.c file. If we do that, then all the list whatever, list create, list destroy, etc. functions would have access to the free list head pointer in common, and there'd be just one free list for them all to share. So we add such a static here to our file, list.c file, and we set it to null so that we have an initially empty free list. Now, we need to modify any point where we malloc or free a node to instead use the free list if possible. So here, for instance, where we free, or here where we malloc. And we could hand modify each case, but it's better to create functions that will call, say, new node and free node to replace the malloc and free calls. All the free list logic can go in these functions. So we would do that, and then down here, for example, do that. And likewise any other place we need to in the code. So let's start with how we'd write free node. It's passed an unneeded node, just like free was originally, and it adds it to the front of the free list. This is the simplest option, by the way, to add to the front of the free list, since it doesn't matter what order the unused nodes appear on the list. One empty bottle is as good as another. So everywhere we call free node, we now call free node of node. So write the code, question 2 now in lecture, write the code for free node so that it adds the node that was passed to it to the beginning of the free list that is pointed to by the variable free list. While you're doing that, I'm going to modify the other free calls here to make sure that we get them all nailed down. So I think that covers them. And then coming back from a pause, assuming that you wrote that free node function, let's put it maybe up here above the list create. This is about what I'd have done. We're going to free node toFree. First job is to point toFree's next pointer to whatever the current first node on the free list is. And then next job is to take free list itself and point it to toFree. And there's our free node call. Now, new node is a little more complex. If the free list has nodes on it, we want to remove one from it, may as well make it the first node that we remove, and return that node. But if the free list is empty, then we want to do a standard malloc call and return the result of that call instead. So, obviously, I'm going to ask you to write the code for new node. Obviously, you're going to have some kind of if statement in there, and you should then, in each branch, either return the first node from the free list, removing it from the free list, of course, or do a fresh malloc instead. And coming back from a pause, there's several ways you might write such a function, but here's a fairly reasonable way to do it. So new node function, and I'm going to have a temp pointer to be the node I'll return one way or another. So if free list, and remember you can use the test directly, and that's essentially saying if free list is not null, then we'll take the first node off the free list and remove that first node from the free list. And otherwise, we've got to do a straight malloc of a node the way we would normally. And either way, when we're done with that if, we're going to have a temp to return. So we do that. And there's our new node. Now we replace all the malloc size of node calls. Turns out there's only one in the add function. And we replace those with new node calls. So now that we've got the free list wired into the code, here's another question for you. How big would the free list be after this series of input commands that I just dropped up on the notes and are in the transcript as well? Brief reminder, by the way, you should be looking at the transcript in parallel with listening to the lecture, but I'll try and cover by putting things in the notes where I can. How many real calls of malloc would have been done at the end of that series of 8 commands? By the way, note the different list numbers. We're working with 3 different lists in list main, and all 3 of them are being operated on here. So coming back from a pause, you should have come up that we would end up at the final estimation with only 1 remaining on the free list, and only 3 malloc calls total, despite doing 5 adds. We'd have an malloc call for each of the first 2 adds, since there's nothing on the free list to start with. But then deleting this one would result in a free list with 1 entity on it, and that's deleting from list 0, of course. And then when list 2 needed to add a node, it would consult the free list and find the one that was just removed from list 0 and use that. No malloc needed there. Free list would then be empty, and the 4th add would actually need to malloc. So there's our 3rd malloc in the entire set, and the last one we'll need to do, because we're going to remove a node from list 2 and another one from list 0, and then list 2 will pick up a node, but the free list will have 2 nodes on it at the time, and so it'll just use the free list. If you think about it, it'll actually be reusing the node we just deleted from list 0, since that'll be at the start of the free list. But again, a node is a node. Doesn't really matter. And the net result is that we will have done a total of 3 mallocs, and the free list will end up with 1 node on it at the end. And finally now, let's make one more tweak to our free list functions. These 2 functions are only needed within list.c. They should not be called or relied upon outside of that file. We can thus omit their prototypes from list.h. But even this doesn't prevent someone from maybe noticing them and declaring their own prototype in order to use them from some other place in the code. To strictly limit new node and free node to list.c use alone, we can add static to their declarations, like that. That static keyword is getting a lot of usage, but if you think about all the cases, static global variables, static local variables, and now static functions, the static modifier always means global but limited to the current file or function. Maybe limited or restricted would have been better keywords for this, but static is what we're stuck with. And by the way, like so many other features in C, this one appears in many other languages using that same keyword, static. And by the way, you may have noticed we didn't add the list prefix to free node and new node. They weren't list free node, list new node, just free node and new node. We don't need to do that because a static function will not clash with same named functions from other files. Its name is only known within the .c file in which it appears. So all that scoping issue is not a concern. Now, let's do one final thing with our free list. In certain cases, a free list can accumulate a lot of nodes, and we may want to clear it of all its nodes, actually freeing them. This is useful at the end of a program, if we want to ensure that all storage is freed and we don't need the free list anymore. We might call a function to do this at the end of main, for instance. Consider what it would take to add a function that clears the free list. Add that to list.c. Don't write the code just yet, but start with this in-lecture question. What parameters, what name, and what return type would such a function have? And in particular, would we pass it a list pointer, like all the other lists such and such functions? Would its prototype go in the .h file? Would it be static? Would it name the, or should it have the list prefix? So coming back from a pause there, the header would be something like void and then list clear list, or list clear free list, I guess. We'll talk about why we have the list prefix on there in a minute, and there would be no parameters. The free list isn't the particular property of any one list, so we don't need to tell list clear free list which list to operate on. Its prototype does need to appear in the .h file, since we call it from main, and that's also why it needs that list prefix. It's not static. It's visible to the rest of the program. And then, just to be complete, question 6 here, fill in the code, please, for list clear free list down in the list.c file. Coming back from a pause there, in fact, it looks an awful lot like the code for list destroy, except that it works on the free list pointer instead of on the head pointer. Scroll that a little to show it. And instead of on the head pointer of some list. So we'll repeatedly delete each node on the free list until we have no more nodes. And there we have it. Now, list clear free list is different from the other list XXX functions, whatever they were, list create, list destroy, in an important respect. It belongs to the list family, and thus it deserves its prefix, but it works on static data, static global data that is the common property of all list variables, and thus it is not passed a specific list pointer. New node and free node are the same way, though the static modifier makes them private to list.c, while list clear free list would be included in list.h, or is included in list.h, and called from outside list.c. And finally, here again we have an object-oriented concept that we can imitate with C. If you're not familiar with object-oriented languages, by the way, it's okay to just get the general impression here. This last paragraph is optional material. But having said that, object-oriented languages let you declare member functions to be static. That keyword does get around, by the way, and in this case it has a somewhat different meaning. These are functions that work with data, like our free list, that is shared by all objects of the type, and they do not work with any particular object. Now, such shared data in object-oriented languages is also termed static. So if you know about static methods and static data in Java or other OO languages, you can mimic them in C using the patterns that we just discussed in this lecture, declaring the data as static global and then the static functions as functions that don't take a specific list pointer or object pointer.